Okay, so this is exam 2 review for dynamics, our dynamics machinery class, excuse me, our analytical dynamics class. We're going to prepare for the final review. In particular, we're going to prepare by looking at Lagrange's equations and the variations in that. For this review, we will treat one example in particular. We'll treat the floating arm trebuchet, use that as a reference. And in this review, we want to review a few things. We're going to review Lagrange's equations. We want to review how we include potential forces. I guess that's part of it. We'll include external forces. We'll consider rigid bodies. And we'll consider Lagrange multipliers. So for our review, we'll grab the trebuchet that we just saw. Oops. I'll stop it there. And the first thing we need to do is create a model, a schematic. So in our schematic, notice we've got the mass going down. So I'm going to draw it okay, like this. So we've got the, here we've got a vertical axis for the slider. We have a horizontal axis. We have this roller, which acts as a point mass. And up here it looks like we've got some mass attached up here and some mass down here. So I'm going to create a schematic that hopefully looks representative. So we'll have our slider with our large mass down here. That's sliding vertically. Up here we'll have another slider or roller. I'll just call it a little point roller, like so. It's forced to translate back and forth. We have a bar that's pivoted on these two and runs on up. And there's a roller there. And out here we have some mass. Let's call this the M sub I for the input mass. We'll call this M sub P for the output mass. We'll call that P and call that I. So we have mass at these two locations. We have the behavior of this system. We'll call this, I guess we can call this total length L. We want to review the various components. Let's start with this basic system and develop the equations of motion for this trebuchet. All right, so the first thing I need is, well, I guess we've been calling step 0, I have to decide my generalized coordinate set. So it looks like I'm going to have a couple terms. I'm going to need some better model of my system to track it through, but let me jump ahead here for a moment. I know I'm going to have some motion, some vertical motion of this guy. I'm going to call that R, and I'm just, R, just scalar R. And then I'm going to have some angle of this arm, call it theta. So I'm going to first start with those two coordinates, theta and R, for my first generalized coordinate set. We'll come back and see that. I'm going to need a vector model for this thing. So let me create my vector model. I had that vector R. So let me call that, or excuse me, length R. I'll call it vector R1. Let's have here some vector R2, and then here's some vector R3. And those three vectors I'm going to use to solve my problem. So it looks like, actually, I should call that length R1. And it looks like I could potentially include R2. Let's start by just including R1 and see where that leads us. So I've got this vector loop model. I know it's a 1 degree of freedom system. And I've got at the moment, I've got 2 generalized coordinates. So that means I have to have 1 constraint in the system. My constraint's going to come from my kinematics, and it's going to come from the kinematics. And in particular, I'm going to use my loop closure, my good friend, the loop closure equation, to derive that constraint. We'll see that in a moment. I think I have enough associated with it. Along the way, I'm going to use, I may or may not be able to, this constraint may or may not be holonomic. I haven't seen it yet, but I'm going to include this using the method of Lagrange multiplier. So I'm going to include into my equations of motion with a Lagrange multiplier. So that'll give me a chance to practice that. So step 1 was choose my generalized coordinates. Step 1 is to get my energies. So it looks like, let's go ahead and carry along the way that this is a rigid body R. So I've got some mass. Let's assume that I have masses at MI and at MP, and then I've got some mass moment of inertia I. I'll just call it I associated with this rod. So my kinetic energy is going to be 1/2 m sub I, v sub I transpose v sub I, where v sub I is the velocity at that point. I get 1/2 m sub p, v sub p transpose v sub p, where v sub p is the velocity at this point. And then finally 1/2 my omega, which is going to be theta dot around the z to k direction, I guess, of the z. Maybe I'll assume this is my n1 and n2. That would put n3 coming out of the board. So maybe I'll say it's about the n3 direction times I omega. So that's my kinetic energy. My potential energy is going, V is going to be from some reference. I'll have to decide where that reference is. Maybe it's here. It looks like it's going to be MIGR1 plus this length up here, which looks like it's going to be L minus R3 times the sine of that angle theta. Now to get T, I need the velocities. And I'm going to try to write the velocities in terms of my generalized coordinates. So V sub I looks pretty straightforward. It's the d dt of R sub 1, which this is on a prismatic, so it doesn't change direction, only changes length, so I'll get an R1 dot in the, looks like in the negative n2 direction. V sub p, looks like I have to take the derivative of these two terms, so it's going to be the derivative of R1 plus this vector L that's running out there, so it's going to be the d dt of vector R1 plus L in the, looks like I'm going to get L cosine theta in the N1 plus L sine theta in the N2. I'm going to take the derivative of that. I get negative R1 dot in the N2 plus a minus L sine theta in the N1, theta dot, L sine theta theta dot in the N1 plus L cos theta theta dot in the N2. I can write that one more time as minus L sine theta theta dot 1 plus L cos theta theta dot minus R dot N2. There. Now, let me go ahead and insert my constraint while I'm right here. My constraint comes from loop closure in this case. And loop closure says that the vectors that form a loop, and let's see them, we wrote them down, R1 plus R3 minus R2 always have to equal 0, the way we wrote them. So vector R1 plus R3 minus vector R2 has to equal 0. I can expand that into my XY coordinates because right now it's a vector equation. I need scalar equations for this constraint. So in the X, or actually I'm calling X, but let's say I've got the N1 and the N2 direction. Looks like in the N1 direction, I get 0 for R1 plus R3 cos theta minus R2 equals 0. And in the N2, I get plus R1 plus R3 sine theta equals 0, plus 0 equals 0. So here I have two constraints, but notice I need a constraint between R1 and theta, and right there I have it. So this is going to be my constraint. That's my constraint equation. All right, now I'm ready to start my Lagrange. So I first say my Q is theta. And I'll just march through my generalized coordinates in turn. So I have Q is theta and Q is R. And since I have two, I think I have room to do them in parallel here going down our sheet. Oh, hold the phone here. We never completed our job of getting kinetic energy. So the kinetic energy is going to be 1/2 m sub I v sub I squared. So that's R1 dot squared plus 1/2 m sub p v sub p squared. So it's going to give me L squared S squared theta dot squared plus that thing squared, L squared cos theta squared theta dot squared minus R dot squared, plus, excuse me, minus 2 L cos theta theta dot R dot, and then minus 2 of those things, so minus 2 L, L sine theta, let's say minus 2 L squared sine theta cos theta theta dot squared plus 2 L sine theta theta dot R dot. Whew. Okay, and then finally plus 1/2 I theta dot squared. Those are my three terms. All right, now I'm ready to proceed. So I need first the partial t with respect to theta. Oh, let's see if we can combine some things. This will just give me L squared theta dot squared. Here I have a minus 2 L cos theta theta R dot, and here I have a plus 2 sine. So that's not really going to combine too much, is it? So I'll just have to plug through the terms. So I got to take the derivative with respect to theta. 0 there, 0 there. Looks like I get a minus 2 times 2, or MPL sine theta theta dot R dot, and a plus there. So get them minus 2 MPL squared cos squared theta theta dot squared. It looks like I get a plus MPL squared sine theta squared theta dot squared. Do that right? That's a minus. It's a plus. Odd the way those terms work out. I was hoping they'd add up. And then finally a plus MPL cos theta theta dot R dot. Whew. Okay, all those terms for my partial of t with respect to theta. Next, I need the partial of t with respect to theta dot. Looks like here I'm going to get a term. I get a MPL squared theta dot theta dot minus L MPL cos theta R dot minus 2 MPL squared sine theta cos theta theta dot plus MPL sine theta R dot, and finally plus I theta dot. Get the ddt of the partial of t with respect to theta dot. Lots of terms, going to expect lots of terms here. So MP times everything. Let's say MP L times L squared everything. Theta double dot. I got to take the time derivative of this, so it's going to give you a minus C theta R double dot over L, and then a plus S theta theta dot R dot over L. Okay, next term. Minus 2 sine theta cos theta theta double dot minus 2 cos theta squared theta dot squared plus 2 sine theta squared theta dot squared plus cos theta theta dot R dot over L plus sine theta R double dot over L plus I theta double dot. Lots of terms. Wow. Lots of terms there. Next, I need the partial of V with respect to theta. Looks like I'm going to get a positive MP L minus R3 cos theta. All right, I'll need to take the I'll need to write the, what about a Q theta? Well, at the moment I have none, so that's 0. And then finally I'm going to need the constraint. I guess we'll come back and do that. Let's complete these parts of Lagrange first. So now I'm going to look at the equation in terms of R. Thank goodness I don't see any R by itself. So the partial of T with respect to R is 0. Thank goodness. The partial of T with respect to R dot. I get a M sub I R dot squared. R dot, excuse me. Side here, I get a plus M sub P R dot for that term. I get a minus MPL cos theta theta dot. And I get a plus MPL sine theta theta dot. The ddt of the partial of T with respect to R dot. I get M sub I plus M sub P R double dot minus plus. Get it MPL times sine theta minus cos theta theta double dot. Then I get a plus MPL sine theta theta dot squared plus MPL cos theta theta dot squared. Partial of V with respect to R is M sub I G. Forgot my G over here. And a Q sub R, again, having no force. Other forces, I'll drive that to 0. Now I need the terms that get associated with my constraint. So my constraint was, let's rewrite the constraint. The constraint was R1 plus R3 sine theta. I need to write the constraint in differential form and actually variational form. And I'll do that by taking the gradient with respect to my generalized coordinates. So I get 1 times a virtual R. So I've taken the entire derivative with respect to R. Now I have to take the entire derivative with respect to theta. So I get a 0 plus R3 cos theta times my virtual theta. And that equals the variation of 0, which is 0. So my component A, I just have one constraint. So A1 R is there and A1 theta is there. Now I write my Lagrange multipliers, or my Lagrange's equation. So on the left-hand side, I need MPL squared times all of this stuff. Do I really want to write that down again? No. I'm going to call this A. So it's A, I'm cheating here, minus this thing. I'm going to call this B, plus MPG L minus R3 cos theta. Okay, now I need my minus my Lagrange multiplier lambda. I just have one of them. Lambda 1 times A1. This is the partial with respect to theta, so it's A1 theta, which is R3 cos theta, equals 0. Now I need the Lagrange multiplier for my second equation, and that is this one I'm going to write out. It's m sub I plus m sub p r double dot plus m sub p L sine theta minus cos theta theta double dot plus m p L sine theta plus cos theta theta dot squared plus m sub I g plus my Lagrange multipliers. I just have one because one constraint times A1R, which is 1, equals 0. So here I have my two equations of motion and my two unknowns. Well, my three unknowns at the moment. Unknowns are r double dot, theta double dot, and lambda. I need a third equation. My third equation is my constraint right here. So I see my constraint, I can plug it in straight away. So R1 plus R3 S theta equals 0. Take the first derivative, R1 dot plus R3 C theta theta dot equals 0. And finally, R1 double dot plus R3, I guess it's a minus, sine theta theta double dot sine theta theta dot squared plus R3 C theta theta double dot equals 0. Wherever I have an R double dot, I replace it with this thing. Wherever and wherever I have an R1, I replace it with this. So that would be my third equation right here. So that gives me my three equations, three unknowns, ready to solve. In this case, lambda is exposed. Now, in this case, the constraint was holonomic. I could write it in terms of the coordinates themselves directly. I mean, we did that right off the bat. So I could have solved for R1 immediately, plugged in the theta term, replaced all my R1s with theta right off the bat. But this method showed us how we could carry through with Lagrange multipliers. The Lagrange multiplier, in this case, is the term, is the force that enforces this constraint. The constraint that R3 sine theta R1 plus R3 sine theta stays as 0. So that I would see that as the force, probably the vertical force in this pin joint right there. That's how I'd read that. All right. So we looked at Lagrange. We looked at the rigid body. We included the rigid body term. We looked at Lagrange multipliers. We haven't had an external force. Let's say, for example, that we decided to add an additional force, F sub t in that direction, non-conservative force. So now I need to add that into my equation. So recall my generalized force, and I'm trying to recall without looking at the book. So now we've got to add it in. So now the generalized force Q is the sum of F sub I times the partial of R sub I with respect to QK, respect to QK, partial R with respect to QK. So in this case, we've got one force, so that's F, it's in the vertical direction, so it's in the negative n2 direction. And we have to dot it, and that's acting on body 1. So we'll have to dot it with the velocity of r1, well, excuse me, the partial of r1 and then I'm going to have to make this as a vector with respect to my qk. Generally speaking, I use the I'll let partial of r1 with respect to qk, I'll use my cancellation of dots and say that's equivalent to partial r1 dot with respect to qk. The partial of r1 dot we said was, we saw it up here, r1 dot was just negative r1 dot n2. So we're going to get 2 terms. We're going to get the partial of r1 dot in the n2 with respect to qk sub 1, or with respect to theta. We'll get the partial of r1 dot in the n2. I think it was negative, wasn't it? With respect to the generalized coordinate, second generalized coordinate, which is r1. This term goes to 0. This term, it looks like, goes to negative 1 in the n2. So we get negative 1 in the n2 dotted with negative f in the n2, so that gives us positive f. So q sub f is our q sub r, and 0 is our q sub theta. So in the second case, f would be our q sub r, and we would include it as a right-hand term, or a minus. If we leave it on the left-hand side, it would be a minus f equals 0. That's how we'd incorporate the force there. Let's say we had a force. What would be a force as a function of theta? I could have a force, I could have a force right here. Let's call that, we're calling that P. Let's call that FP. Let's say it's always perpendicular. So to find the generalized force associated with that, now I'm considering the FP. I would have my my Q sub K would be the partial, sum all the forces. So now I'm considering the FP dotted with the velocity, dotted with the partial, okay, and that's vector FP, dotted with the partial of that R sub P with respect to my little QK. F sub P is, it looks like, is always in this direction, perpendicular to that rod. This direction is theta. This direction is theta minus 90. So it looks like it's cos theta, FP cos, it looks like it's FP is, vector is cos theta minus 90, cosine theta cosine 90, plus or minus sine theta sine 90. So it would just be sine theta plus, that'd be the x term. Y term is sine. Sine of theta minus 90 is going to be sine theta cosine 90 minus cosine theta sine 90. So it's going to be minus cos theta FP in the N2. And then my R sub P, we already saw, was R1 plus L. This vector R1 plus vector L. And the velocity of P, we saw it above. We use the cancellation dot. So it's negative L. Let's see if we can just copy this. Okay. So our V sub P is this. The partial of R with respect to QK by cancellation of dots is, and this RP, is the partial of V sub P, which is our, what we're calling the time derivative of that, with respect to Q sub K dot. So we'll need two terms. We'll need the partial of V sub P with respect to R1 dot, and we'll need the partial of V sub P with respect to Q theta dot. Partial with respect to R dot, you can see is right here. We'll get this negative 1 in the N2. Partial with respect to theta dot will give us a negative L sine theta in the N1 plus L cos theta in the N2. We'll dot each of these with the forces in turn. So that will give us effectively our Q sub R will derive from this. So Q sub R will be this term here dotted with F sub P. So it's an N2 dotted with that N2. So it's going to be positive cos theta F sub P. Our Q sub theta is going to be the V, this term dotted with this guy. So I'm going to get two of them. So I'm going to get F sub P times minus L sine squared theta minus L cosine squared theta, which is just FPL. It's my Q theta. Okay. Well, that's a fairly complete review. We've considered, and then of course we had these terms in. So let's go back and see what we've considered again. We looked at Lagrange, considering external forces, rigid bodies, Lagrange multipliers, Lagrange's equations. We have to choose our generalized coordinates, write our energies, take the partials, and then combine according to Lagrange's equations. For the external force, we looked at two forces, one force acting here, one force acting here. Recall the equation. The generalized force is the sum of forces acting in the bodies dotted with the point at which each force is acting, partial with respect to QK. Use the cancellation of dots to say the partial of R with respect to QK is the partial R dot with respect to QK dot. We have to do that for all K and then dot it with each force. That gives us our Qs. We did that over two examples. We considered a rigid body. The rigid bodies show up in the kinetic energy. We have to recall the terms to write the energy for rigid bodies. And finally, we looked at Lagrange multipliers. For the Lagrange multipliers, we had constraints that weren't subtracted out in the generalized coordinates. Here we had a constraint, was the fact that we had a mechanism. It's a 1 degree of freedom mechanism, but we chose two parameters to describe it, theta and R1. And we described it with those two parameters, but there's only 1 degree of freedom. There has to be some constraint. For these mechanisms, loop closure is always the constraint we can write, which is that these three vectors have to stay closed. So this is just a fixed point. This bar slides horizontally. This bar slides vertically. These 2 points are constant length apart, so that creates a loop. And I write the loop equation. That actually yielded two constraints, notice. There was a constraint 1 and a constraint 2. Constraint 1 related R2 and theta. Constraint 2 related R1 and theta. Let's say, hypothetically, I chose Q, my generalized coordinates, to be theta, R1, and R2. Well, again, for a 1 degree of freedom system, that would imply I need two constraints. And here are my two constraints. I could plug these. I could either plug these in directly here and get all my terms in terms of theta, or I could just incorporate them with Lagrange multipliers. To do that, recall, I take each constraint multiplied by Lagrange multiplier. I have to write the constraint in the variational form. I did that down here. And then the coefficient of the partial of R term gets multiplied by the Lagrange multiplier in the R term. The coefficient of the variation in theta term gets multiplied by my Lagrange multiplier in the theta term. And finally, well, that's everything. Okay, that concludes this exam review.